questions from homework first thing? Take this somewhere. Are we ever going to get into those? Huh? Yes, we'll get to the fundamental theorem of calculus.
Oh.
Any other questions? Is anybody here who didn't get their test back yet? Tom, right? Yes, sir. Anybody else? Okay. Is there anything from homework? Okay. So let's see. Last time we got into the idea of finding the area under a curve. So I've got this. Let me think about how I want to approach this. Let's do one more example, and then I'm going to have you guys. No. I'll tell you what. Let's do this one together. This will be nice. The graph is on here, so I don't have to rely on my other board graph. My graphs make you feel like
It's also easier to see it.
you need glasses, or if you have glasses, you need to change your prescription. Oh, one more.
Now, what do you mean by the
That's so nice. Oh. Alright. So obviously you don't know how to do the last thing on the sheet yet. Okay. So I'm going to try to be a little technical so that we can get into the next level after this. Too bright. Can somebody dim the lights a little bit? One of those turns out. There you go. That's good. Is that all right? You guys all right?
That's good.
Ooh, okay. I'm not going to bring out little candles. Sorry.
That'll be cool.
Yeah, I would. Welcome to calculus, sir. Can I just sit all right.
Calculus.
If probably any one of these.
Yeah.
Oh, that's mine. All right. So if we're trying to look at this function, so I've graphed it for you. I want to draw 6 rectangles in from a equals 1 to a equals 4. So I want to do the area below this function between 1 and 4. So that area right there, right? I should not have just drawn those lines in, but I'll get over it. Oh, all right. So that should tell you to take those out if you drew this one. I want to draw 6 rectangles. So how wide would each rectangle have to be? Well, how far do I need to go total? 3. So that's why this is the formula there. I've got to go 3 over, and I've got to fit how many rectangles into that distance of 3? 6 rectangles in, so my width of each rectangle is going to be 1/2. So if I'm using left endpoints, which means when I draw my rectangles in, the height is going to be governed by the left output. The left side of the rectangle's output. So this first, and let's try this. Each rectangle is going to be 1/2 wide. So the first rectangle is going to start at 1 and end where? 1.5. I like it. Then let's go from 1.5 to 2 to 2.5, 3, 3.5, and then it's going to end at 4. I like it. Okay. So some of you guys might realize why I wish I hadn't drawn that in, but too bad. So the first rectangle, let me go ahead and draw it in. This is going to govern the height, the left part of it, and then I'm going to draw it over to there. So it's got a width of 1/2 and a height governed by its left side. Try to draw on the next rectangle. Maybe use pencil just in case. You guys really able to see okay?
Yeah.
Okay. Can you, are you okay with taking 2 classes at once? Is that right? Just doubling up on your money? I like it.
As long as
It's the same class again, isn't it? Alright.
Yeah.
So this rectangle, I want to go from 1.5 to 2, but again, the height's going to be governed by the left side, so I'm going to go there, like that.
What are we doing?
Yes, thank you.
Alright, let me stop there for a second. What's up?
What do we do at the top? Do we still govern for the left side? Or
The top? How do you mean?
once we get to 3?
Every rectangle I'm drawing, since I'm doing the left endpoint approach, every rectangle has to be governed by the left side of the rectangle. The output for the left side is going to be how tall it
And
is.
it's going to eventually go outside the down.
Well, yeah, so since this is a symmetric graph, if I would have went from 1 to 5, let me see if you guys get this. My left endpoint and my right endpoint would have been equal because it's symmetric already. So that's why I didn't do that. I went to 1 to 4. Screw you, Jeff. So far I've got a what kind of estimate? Underestimate. I like it. Kick ass. So the next rectangle governed by the height at 2. Are you guys kind of with me here?
Yeah.
Alright. And then this one is governed by that. And then at 3.
Whoa.
And then there.
That was a part of my mind.
So again, the way you do it is wherever the left is, you go to where its output is, and then you just draw straight over from there. I mean, I agree with you that actually, I can still feel it too when I make that transition from under to over. Your brain's like, alright, I understand that. But that's kind of nifty. Or at least I think so. I don't know. So somebody help me out. What is the area of that first rectangle?
So 25 times 1.
Yeah, the height is 1, and the width is 1/2. I love it, right? Plus second rectangle. So let me say this in general. In general, it's going to be the area of each rectangle is going to be the width times the function evaluated at xi. So this is where I want to be a little more technical. It's okay. There you go. All right. So x1, not surprisingly, is 1. What's x2? 1.5. I love it. x3, x4, x5, x6. 4 is not x anything. 4 is just where I stop. It doesn't govern the height of any rectangle. So if I was using right endpoints, x1 would have been x1 1.5. The first rectangle, I understand what you guys are doing. You're trying to start from that. The first rectangle would have been governed by the height here. Right? So x1 would have been 1.5. And then the last x6 would have been 4. So we're going to see that in a minute, obviously. I've got the other one for the right endpoints. Okay. You guys with me so far? A little bit?
Yeah.
Alright. So now I can see that when I want to rewrite this, let me see if you guys are cool with this. Does this ever change?
No.
So I can write that width just on the outside. I'm going to factor it out. Is that cool? And on the inside, I'm going to have a bunch of these added up. So I need f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. You guys see what I'm doing?
Yeah.
Yeah, Jeff, you write a bunch of shit down. Yeah. And you want to make sure you have how many f's in there? So correspond to my 6 rectangles, because it's real easy to just go to 4, because your brain's like, I got to go to 4. And you're like, no brain, 4 doesn't tell me anything about a rectangle. You guys with me? So there's 1, 2, 3, 4, 5, 6. Good check to do, trust me. Because as a human, you want to go to 4. Well, we do get to 4. That last rectangle does get to 4. So now you just got to plug and shove. Now you just got to figure out what those function values are. So we know the first function value is 1. That's easy enough. 1.5, it looks to be 3. Can somebody figure that out real quick?
It's 2.75.
2.75? Good. So we're close. That's what f of 1.5 is. Now you throw a 2 into the function. This is almost too easy to believe, maybe, that if you understand that these rectangles are, their height is governed by the function outputs. That's why all I got to do is throw a bunch of things into the function. And their width is governed by how many rectangles you want to use. So this should be remarkably simple math. So 5.1 is simple. So if you're thinking like this is too easy, good. That's the way you should feel. 5.2 is where things get weird as hell, because that's when we let our number of rectangles go to infinity. We ain't got to be drawing a picture for that. All right, and you keep going. F of 2 is what? Is it 4? No. Let's see. What's f of 2? Negative 4. Negative 8. Yeah, it is 4. Thanks for all the help, guys. 2.5. I'm not going to do that one in my head. Is anybody able to do that? 2.5. Can you throw that into the function? Anybody?
I got 4.75.
4.75.
It's pattern.
Dude.
Start guessing.
And then f of 3. 6. And then, is it? Oh, you. Let's see. So f of 3 would be negative 9 plus 18 minus 4. So what is that? 5. Look how close you were, man.
Last one's 5.75.
Well, you're funny, because isn't that about where it turns? 3 is the vertex, so the next one is going to be this repeated again, isn't it? Oh, snap. So plus... Okay, cool. Is it always going to work? No. It depends on what your function is. The function can be freaky as hell. You can't have any pattern, too bad. But parabola is hell, yeah, you got some patterns you can use. And then, help me out, what does all that come out to be? I don't mean just read it to me. 11.125?
The after you divide it in half?
Let's see.
Yeah.
Yeah, it looks like 3, 7, 12, 20. Yeah, it looks like it's divided in half. Cool. Anybody else get that same thing?
11. Yeah.
You're all like, that sounds good, Jack.
I believe her.
Who needs to She sounded like she knew what she was talking about. Alright, so that is the official formula we just used. So if we look at this real quick, I want to get you guys started to be used to this summation notation. Each rectangle looks like this. The height times the width. That is amazing, right? That's beautiful level of mathematics. Geometry. This tells me I'm going from 1 to 6, which makes sense because I want 6 rectangles. So if I'm using left endpoints, I've shown what my x1, x2 is going to be, right? You guys have seen summation notation before. You must have. Right? It's supposed to be in pre-calc at the end. All right, even Math 110 sometimes you do it. So what this means, for example, so that's what leads me to this. That says add up the width times the height for each rectangle. And that's exactly what we did. Right? I factored the 1/2 out. You can always do that. So in general, if I had, for example, let's just look at summation notation by itself. I equals 1 to 4 of I squared. So what's I going from to?
From 1.
From 1 to 4. So what is I first? 1. And what's the value of this at 1? 1. Plus, because it's the sum.
Plus 4.
Now I becomes 2. 4. Plus 9 plus 16. Alright, so does everybody get that basic idea? That's what sigma notation represents, is it says sum these up. So this says sum these. Each of these is a rectangle area. So that's what we did. We added up all those 6 rectangle areas. Okay, maybe.
It's like rectangle 1, 2, 3, to 6, right? It has nothing to do with x's. Like x.
Well, this little x dude, this is x1 for the first rectangle, x2. So this becomes x1, x2, x3. So I could say this is f of x1 times delta x plus f of x2 times delta x, so forth. And then we just factored the delta x out, right? Because they each have a delta x, I could factor that out. And then it's just f of x1 plus f of x2 plus f of x3. Those sums. Is that all right?
It was a question, but yes.
Oh, sorry, buddy. I like to answer the question I hear. So 10 and 20, 30. That's amazing. So let's do this again. You guys try to draw in the rectangles for right endpoints and try to do that math. Second?
It's the same function.
Same function, yeah, exactly. Yeah. This is all about the same function.
It's still 1 to 5.
1 to 4.
It's still 1 to 4, yeah. So what are we doing? We just did left endpoints, and we know, can you guys tell me, it was mostly what kind of estimate? Mostly it was under. When I do it for right endpoints, it's going to mostly be over. So when I average those together, I should come out to decently close. And then I'm going to show you the shortcut on the calculator for checking this kind of thing. All right, let me see. There's a couple of easy mistakes you can make, but my first rectangle has to start where? At 1. Because I'm going from 1 to 4. But the height of it is going to be governed by this. So I draw up and then over. I've got to go from 1 to 4, right? So you have to end up covering 1 to 4 with rectangles. So then the next rectangle is going to be governed by the height at 2. And then at 2.5, 3, 3.5. We get the idea, Joe? Okay. So that one is mostly overshooting it. So that's why the average comes out pretty nice. So now to set this up, just do the sum I equals 1 to 6 f of xi delta x, which will be f of x1 plus f of x2. Blah, 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 taking out a delta x. All right, how are we doing there? Is that cool? Mm-hmm. There are methods where you can have the width change. Not all the rectangles are the same width, and believe it or not, there are situations where you have to do that. But thankfully, we're just letting the width's the same. We can factor the damn thing out. That makes this a lot easier. So then I want, and that, you can notice it's beautiful when they ask you to do both left and right endpoints because I've already got a lot of these function values done. Right? So I want f of, now what's x1? 1.5, the right endpoint now. Plus f of 2, plus blah, 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 blah. Times 1/2, because that's the width. Alright. So we've already got some of these values from before. We got 2.75. Where'd it go? 4, 4.75, 5, 4.75, and then probably 4. That's crazy. If you plug all that in the calculator, has anybody got that yet?
12.625.
12.625?
Yeah. Anybody else want to verify?
Kevin's like, bring it.
No, I just want to be sure.
Bring it. Oh, be it. Let's see what you mean. So, let's see, minus 0.5 plus 2, so plus 1.5. Yes, that's right. What am I doing? I knocked him out, so I lost a half, and I added another 4, so I gained half of 4 too. I lost a half, gained 2, so overall I gained 1.5. 1.5 plus this is this. Or just plug all that shit in. That's fine. What's the average of the two numbers we got?
11.875.
11.875. So that is our official best guess based on using 6 rectangles. 11.875. So here's the really cool thing. I love the visual of this. If you have a calculator, I didn't bring any, so if you don't have one, too damn bad. But, or whatever you got. I think even a TI-82 could do this. So first thing I'm going to do, obviously, is tell it what I'm freaking using as a function, negative x squared. Should probably let the calculator in on what I'm doing. Alright, so I'm using this function. Wow. That's awesome. You sound like the little things from Toy Story. The calculator. Now that was just weird. Alright, so now let's hit zoom 6 so we get a nice. Alright, so there it is. Oh crap, sorry. Oh, sorry. Every button is doing the same thing now.
Well, you had it too. Okay, that's okay. Don't mess with it.
You tell me not to mess with it. Now, I want to show you this. It's a little bit early, but I already showed you the symbol. You've already seen the symbol like on that side of the board there, right? And that will be related to that. Well, I can say this directly. That is the area under a curve. That's what that represents. We still have to prove that it's related to the antiderivative. That integral, that big elongated S, that is actually exactly what that symbol is. They said it's a sum of areas inside of a little a curve, right? So that's why they used elongated letter S. That's exactly what it is. If that's what it looks like, hey, that's what the hell it is. So watch this. If you hit second calc, and here you can get the value, you can find the roots, you can find the min and max, right? Look at number 7. Well, look at number 6 actually first. Haha. Look at that was evil. Read your manual. Look at number 7. So if I hit number 7, it's going to ask me, obviously it's going to ask me, where do you want to go from to? So if I hit number 7, it's going to say lower limit, 1. Upper limit, what was it, 4? 4. This is going to be infinite rectangles. That's what it does. It does infinite rectangles. This is the exact answer, and the exact answer is 12. It's really cool. I love the visual. You can see it get filled in. That's the area it's finding. Are you guys kind of with me?
Yeah.
That's an awesome little visual of what's going on. The actual answer is 12. Our approximation was 11.875. I'd say that's pretty damn good for using 6 rectangles, right? You guys still with me?
So the more rectangles
you use, the better your approximation should get. Exactly.
And you still need to do left to right and then average them.
Alright, so now that we got left to right, there's a method called midpoint. So what does that sound like it would be? That's crazy. So if I wanted to use midpoint, my first rectangle still has to go from 1 to 1.5, but what's the midpoint?
1.25.
Try one more time. Yeah, 1.25. So then the height, don't try another time, just try another time. The height would be governed by the midpoint. So now when I go to set up my, and I could keep drawing this, when I go to do my sum, it would be, there's still 1/2 wide, but now it would be f of 1.25 plus f of 1.75, because they're half, they're each 0.5 wide, right? And so forth, so forth. If you do that, you should get the same thing we just got, 11.875. Because the midpoint basically is like the average of the left and right endpoint. So its output should be close to what you get when you average the left and right endpoint. How are we doing there? Is that...
Or you do that.
Huh?
Did you that instead of 11 unless you're
I don't want to do it. You can do it. Right? If you did... Yeah. I thought you were like... You're like... Do it. It's your job, man, Matt boy. I was like, shit, you know? Sorry. If you did it, yeah, then it would come out. Yeah, so some of the homework has you doing left, right endpoint. Some of it's got you doing midpoint. I like it. Cool. I like it. All right. So let's go to the next level. Whole level. Well, you know the next level. I've already been telling you the next level. The next level is doing all this, but letting the rectangles go to infinity. So can we crank the lights back on? Can we? Yes, we can. That's funny. Bright light. Okay. All right. So, a couple things we got to know. Why does it still look? Can you crank the other one up too? Are you like adjusting us up? And then the other one. No. There's two of them. There it is. All right. No. I'm gonna mess with him. All right. So there's a couple things we got to know going into this. One of them is this here. Oh, down there, Jeff. Let me just write this down and see what you guys think about it. All right. So a couple things. That I, remarkably enough, is very often called the index. It's like a variable, but it's a variable that's controlled by these, right? So I goes from 1 to whatever, like we had 6. So what's going from to now? From 1 to n, kick ass. So, and of course C is pretty much always known to be a constant. So if I add a constant n times, so if you added 3 7 times, what's the quick way to do that? 3 times 7. It's great. So if you add C n times, you'll get NC or CN. Yeah. Let's make that just an endless single. Or a critical number, right? But yeah, Cartoon Network, a little less calculus, you understand. And a lot. No? Johnny Bravo? So what if I do this? This is where things get interesting. It's not an easy one. I'm not claiming that.
n squared.
No. So let's prove. Let's prove what it is. So basically, here's what it could be. Like if I'm saying, let's say the sum I equals 1 to 100. Let's make it a little bit more manageable, right? Just 100. Just 100 numbers. You cool with that? I don't care.
Just 100.
Just 100. Because how many is this? It could be an infinite number. So maybe less than that. So what does this look like if I wrote it out? What's I at first? 1. And then it becomes 2. That's crazy. And then it becomes, that's crazy. Let's skip a little bit. Then it becomes 97. All right, so do me a favor. Go ahead and add those up. Nobody moves. That's the perfect reaction. So this is I didn't tell you about this yet? I guess not. I haven't had a reason to. There's an urban legend in math, and it's not got anything to do with kidneys being stolen or anything. It's Gauss was this guy Gauss. He did a lot of shit in mathematics and physics. His class, when he was like 10, his class was being unruly, and the teacher's like, "You will add up the numbers 1 to 100 now." And the teacher sat down. He's like, "That'll give me some time." Little Gauss dude, little smart ass, he's over there. He's like, bam, I got the answer. Bam. Like 5 seconds later, he's got the answer. And his teacher's like, holy shit. So the teacher checked it, sure enough. And what Gauss had realized is 1 plus 100 is 2 plus 99 is
101.
And how many of those am I going to have? There you go. 50. Why 50? Because I got how many numbers? In general, n, right? So n divided by 2 is how many pairs I'm going to have. And the sum is always going to be the same thing as the first number plus the last number, right? So what is the sum of I equals 1 to n of I? It's this. It's n over 2. So let me write this a little differently. N plus 1. Now, does anybody realize what that comes out to be? What's 50 times 101? 50-50. You're going to love that. The sum of the first 100 natural numbers is 50-50. 5,050. Yeah, that's kind of nifty on its own. It's like, okay. All right, so this is true, period. Let's try it. Let's try it. What's 1 plus 2 plus 3?
3.
I could almost see something going. I'm going to start the big one. It's like, shit. Alright. Now, if I plug it into this formula, what's n for this? How long is this list? 3. So sure enough, if I put 3 over 2 times 3 plus 1, what's that? 3 over 2 times 4. 2 goes over 4 twice. 2 times 3 is 6. So that's not a proof. That's the proof, but that's an application of it. Right? How are we doing so far? Are we decent? Let's see. I hate Thursdays. So now we got this here. I think the book puts it like this, but it's the same stupid thing, of course, right? And then final.